So we'll be discussing virtual work. Right? So in the virtual work, right? So before starting virtual work, we need to understand what is work. What kinds of work section we can expect from the scenarios, whatever we have learned till now. So once we got an understanding of that, then actually we can see what is the virtual work, right? So in that actually, it is work. Right? So the work meaning, like actually suppose if I lift this chalk piece, so you can say that actually I have done some work, right? So suppose actually if I move from here to here, then actually we can say that I have done some work. That means in every part of the work, if you notice, there are two important fundamental quantities that are there. So one is there has to be a definite displacement. And this is one fundamental quantity. And another important quantity is to have a displacement, so there has to be an applied force. So any activities which will have both of these components, we call that as there is some work that is done. Yeah, just a minute. Yeah. So these are two important fundamental quantities. If at all actually these two components are involved in any particular activity, we say that there is some work. Suppose actually if I try to move this board like this, but actually whatever may be the applied force I have, so this is not at all moving, right? So in such cases we can simply say that there is no work done irrespective of whatever may be the force I applied, right? And without having the force, right, there has to be, so there won't be any displacement at all. So in that case also we can say that there is no work done. Now actually to quantify the work, so based on these two important quantities, right? So if I say that suppose I moved this chalk piece from this place to, let us say 100 kilometers, actually I have taken this chalk piece. And then actually there is one more person who tried pushing the car for a distance of 1 kilometer. Now actually who has done more work? One person actually tried pushing the car for 1 kilometer and another person actually took this chalk piece for 100 kilometers. Who has done more work? How can we justify that? How can we justify? Who has done more work? Now actually here both are, yeah. So both are important, not the displacement, not the force. So for moving the car actually we have to be applying more force. And for moving the chalk piece actually we have to be applying very less force when compared to the moving of car. Now, but the displacement wise, if you notice, the car has moved for a displacement of only 1 kilometer, but this has done actually a displacement of 100 kilometers. That means to quantify the exact work in first case, right? So W1 is equal to F1 into R1. So F1 is the force applied in the first case and R1 is the displacement that got established. Now W2 is nothing but this is F2 into R2. Now W1 and W2. So depending upon this product, we are going to quantify whether W1 is greater than W2 or W1 is less than W2, like this. Now actually when we do this, right, there has to be one more important quantity, that is the direction of the force. That means suppose if there is a body like this, on this body let us say I have applied a force of F like this, and then the same body, now actually I have applied the same quantity of force, but it is making an angle of theta. So this is also F. Now this is also moved for a distance of R again. So this is also moved for a distance of R. Now which one is having more work in both the cases? So this is more work or this is more work? Who has done more work? So the first one is having the more work. Why? Because see this, I will say actually one more important test. So let us say this chalk piece actually I moved from here to here. Then actually I have done some work. Now actually the same chalk piece, if I try to move like this and bring it back to the same place, then actually what is the essential work I have done? If I bring back to the same location, So obviously it is zero work. Why? Because there is no displacement. That means actually, suppose if I say simply like this, so I ask actually one of my student to move this board or move this chair from this location to this location. Then actually I went out. Then by the time I come back, he moved the chair from that location to the next location, and again he moved back to the same location. Then when I come back, right, if I notice the chair is there at the same location where when I went, right, that means I feel that actually there is no work done. But in reality, actually he has done some positive work and some negative work. Both together are compensated. So I feel that actually if the chair is moved from the location A to location B, I feel that actually he has done some work. But actually he has done the negative work also. That's why actually we feel that he has not done any work. So the work is always conservative. So why? Because as long as there is a displacement, then only we say that there is some work. Now in this particular case, the force that is applied, right, it is directly useful in moving this body. But in this case, the force is directly not useful to move this particular body in this particular direction. But there is certain component of the force actually, that is F cos theta, is the one actually which is essentially used to move this body from this to this. That means if you notice this one, W is equal to the force into displacement, and here W is equal to F cos theta is the essential force and the displacement. So this is a modification, and this is applicable for any angle theta. This is applicable only for the zero angle, wherein the force direction and the displacement direction are one and the same. If I draw the vectors, so this is F vector and this is R vector. So F vector and R vector is making an angle of 0, hence the cos theta value is 1. So cos 0 is 1, hence actually we can say direct product. So that's why in the early standards actually we say that work is nothing but the force multiplied by displacement. But ideally a dot product of F and R. So that is the correction from the previous ones. So F is equal to, W is equal to F into cos theta into R. So in short, we call this as F dot R. So this is the work. Now work is a scalar quantity, but F is a vector quantity and R is also a vector quantity. Now actually the product of two different vectors actually coming out to be a scalar. How can it be possible? How can it be possible? The product of two vectors coming out to be a scalar. How can we justify the case? How can we justify F dot R? Both are vectors coming out to be a scalar. By definition, scalar is not having any direction. Any physical quantity which is not having a direction but definitely having a magnitude is called a scalar. Now here actually these are the vectors. Both magnitude and directions are present for both F and R, right? Yeah, work has no direction. How can we conclude that? From this product of two different vectors actually, how can we say that a scalar quantity that is definitely coming? That's the question, right? Work has no direction. Because of this reason only we concluded that work has no direction, right? So why? Because see this, the applied force is this direction and the displacement direction also the same direction. Now when both are happening in the same direction, then actually where is the need to specify the direction? Because both are in the same direction, right? So when both are in the same direction, there is no need to specify the direction there. Hence it is a scalar. Even here also the essential so this is the force direction, but the component of the force which is useful to move this body to this location is F cos theta. Now F cos theta direction and R direction are one and the same. So the component of the force which is useful and the displacement are having the same direction always. In any dot product actually it is the case. Hence you don't need to specify the direction for a dot product. Hence the result is coming out to be a scalar. Got it? Understood? Right? So this is the essential thing. Now actually, okay, so I hope you understood this concept. And there is one more thing called work energy theorem. So what work energy theorem says is, so work and energy, what is the difference between these two? What is work and what is energy? What is the difference between work and energy? So when we calculate, right, we always calculate the work. There is no method to calculate the energy in physics, right? We always calculate the work and we say that actually the same work actually is stored in the form of energy. So we are calculating work, but not the energy. But we treat that as energy. Why? Because there is something called work energy theorem. So work energy theorem. So this work energy theorem says, so if there is some work done, the same work is getting stored in the form of energy. So that is work energy theorem. That means, suppose if I take this particular chalk piece from ground to this location, I have done some work. Why I have done some work? Because there is a gravitational force which is dragging this towards the ground. So because it is dragging towards the ground, I am applying my force against the gravitational force for moving a displacement of this height. So that means there is an essential force that is applied and there is a displacement that happened. That means I have done some work. Now, because of that, what happened is this chalk piece has got some energy. That energy is in the form that actually we say that it is the potential energy. That energy is responsible that if I leave this chalk piece, it automatically goes down. So it has got the ability to move back. That ability is coming only if I lift. Otherwise it won't, right? So for lifting I have done some work. If I leave it, it has got the energy, that's why it is going back. That means this energy, whatever it got, the same energy is the work whatever I have done to lift this chalk piece, right? And this is what is called as the work energy theorem. And if you notice, to have an energy, there has to be an always counter force. That means if I move this chalk piece to the top, so let us say this is the movement. Now, there is a restoring force always. So this is the restoring force. This is the restoring force. Now, this is the upward direction is the applied force. You are doing work only when there is a restoring force, right? So this is the restoring force. You applied a force which is opposite to the restoring force. Hence, you have to do work, right? Hence, you have to do work. Then only you will be doing the work. And the same work is getting stored in the form of energy. As and when you move this, or as and when you leave this force, right? Automatically, this restoring force will bring back to the original position. And this method of coming back to the original position, right? So is called as the storing of energy. So if you apply the force and move to a certain location, there will be certain energy that is going to be stored against that, as long as there is a restoring force. Got it? Understood or not? So if you take spring action also, if there is a spring like this, now actually this is the body. Now if I move this body to this location, automatically it will come back because there is a restoring force always. And while moving this particular body to this location, I have applied a force of F. And let us say this is moved for a distance of x, then F into x is the work. Got it? F into x is the work essentially I have done. Same work is getting stored in the form of energy. Right? So that is spring energy, it will bring back again. So that's why work energy theorem says that as long as actually there is a restoring force, if there is some work done, then automatically the same work is getting stored in the form of energy. Got it? So that's what is the potential energy which we have got by virtue of the displacement from one location to the another location. So if you got some energy by virtue of its displacement, then it is called the potential energy. If you got the energy by virtue of its movement, then on movement I mean if because of certain velocity, we say that there is some kinetic energy. So there are n number of forms of energy, but in kinematics or actually in mechanics, we deal with only two different kinds of forces, only two different kinds of energies, that is the potential energy and the kinetic energy. Got it? In fluid dynamics, actually along with these two, we are going to add one more energy, which is the pressure energy. So these three are getting related, which we call as the Bernoulli's equation there. So essentially in physics, the fundamental principle is the conservation of energy. That conservation of energy will drive entire physics, including our statics and dynamics. Got it? So that is the basic principle. You can note down this. Got it? So now actually, so in statics actually, So there is only one fundamental quantity which we are dealing with, that is the force, right? So because of the force, actually there are two different kinds of displacements that are happening. That is, suppose if I take this particular body and on this body if I apply a force like this, then actually there will be a linear displacement. So this is usually represented with a letter of U. And suppose, as we are dealing with the forces, right? Suppose actually I have one more force, F1 and F2. So because of these two, actually there is a linear displacement. Now, one force is applied here and another force is applied here. Then actually, let us say these two are actually equal in magnitude. Let us say F1 is equal to F2. Then this will be purely rotational, right? So this is as if like there is a movement. So if there is a movement, then it will try to rotate here itself rather than moving from this location to this location. Now in the first case versus second case, suppose if I take this as the origin, so this is x-axis and this is y-axis. Now with respect to this origin, so this is having the center of gravity is having a coordinates of x1 and y1. Now after the application of these two forces, so the center of gravity of this particular body is moved to this location. That means this location and x2 and again y1, right? x2 and y1, right? Or else actually even if it goes diagonally also, there will be x2 and y2, but the condition there is this is being a rigid body. I explained what is rigid body. Rigid body means under the application of the force, the internal molecular displacements won't change. That's what is nothing but rigid body. Now here actually, even if I move this place to this place, so let us say one particle is at location here and another particle is at this location. Now let us say the distance between these two is p, and even after the movement to this location, again the distance between these two again p, it won't change at all. And this is what is called the rigid body, right? The displacement won't change. Now it doesn't matter whether the particle moves in this location or in this location. Suppose if it goes radially like this, then actually, so this is the location and the particles are having the same location again. But the movement is linear and it is moving like this. As long as this body is exactly the same rectangle or actually same cuboid, whatever is present here, without making any rotation, if it moves to a different location, then we call that as a linear displacement. So here the linear displacement is here to here. So this is the linear displacement. That means first center of gravity to the second center of gravity is called as the linear displacement. Now suppose if I take the second case, what is happening is the same body is present here, but after the application of these two forces, so it may go like this. So the center of gravity location is initially x1, y1. Even after the application also, this is x1 and y1. So even after the application of the force also x1, y1. That means center of gravity is not changing here. Now this is called purely rotational. Now if there is purely rotational, then actually can we say that none of the particles of this body is moved? Can we conclude that way? None of the particles of this body is moved. Because the center of gravity is same in both the cases. We cannot. Right? So though entire body, if you consider it, so there is no movement, but internal particles of this particular body are oriented now into a different location. But internal displacement, suppose if I take these two particles, so the same two particles which are present here, now after the movement actually are present here. The displacement between these two also again same. But when I look at from here, this is actually onto the top. Now actually this is rotated like this. Let us say this is like this. Now if I look at this location, the particle, right? So here I say that this particle is top of this particle. But here I say that this particle is at the left of this particular particle. That means the way I express or the way I describe the particle is different there. But the distance between these two is again the same. So being this is the rigid body, so no particle displacement will be there, but the direction of the individual particles are going to be changed. So this is in the case of purely rotational. And to calculate the rotational quantity, right? So we have adopted the procedure of calculating the moments. So in statics, we dealt with two different quantities. One is resultant force R and the resultant moment G. So R is to what kind of the body? To have a linear displacement. And G is to move the body in a rotational manner. So this is responsible for linear displacement. And this is responsible for rotational displacement. Right? So till now actually whatever we have learned in case of equilibrium of body, whether it is 2D or 3D, right? So we always dealt with a case of where the system is under equilibrium condition. That means essentially no movement and essentially no displacement. So such kind of cases actually we have analyzed. Now this case actually, if there is a displacement, how much it is going to be? So that is the kind of scenario what we are going to deal with. So because of the force, there will be a movement obviously. That movement actually will be elaborately analyzed in case of dynamics. Now here actually we are understanding what is work and how much is the work we have done. To understand the concept of principle of virtual work, this principle of virtual work actually will be useful in identifying the unknown forces, right? So not to analyze the movements, right? So in case of dynamics actually, the effect of all these forces together actually will be responsible for the movement of the body from one location to another location. Now here, there also work is done, here also work is done. That work concept actually we are going to use to find out the unknown forces with the help of principle of virtual work. First of all, we need to understand what is work, hence this discussion. Got it? I hope you understood this concept. Right? Now actually we have to individually calculate what is the work done in case of R and what is the work in case of G and what is the work done in case of both. Got it? So if R and G both are present, then actually this is the linear displacement, this is the rotational displacement. If both linear and rotational are present, displacement are present, then we call that as a general displacement. General displacement. Got it? Yeah, you can note down this. So let us say this is some origin and then this is x-axis and this is y-axis. Now this particle which is located at a position vector of r1 or r, and then the same particle is moved to a different location like this. This is R2. And then let us say if R1 is equal to R2, R1 equal to R2. That means this is just a simple radius. So this is R and this is also R. Now this particle is moved from this location to this location, right? So this is moved from this location to this location. Let us say this is P and this is Q. Now what is the linear displacement it has with respect to this origin? What is the linear displacement? How much is the linear displacement it had? Or if I say that, no, it's not R2. So if I say that, what is the radial displacement? Radial displacement is the linear displacement. What is the radial displacement? That means this location from here versus here, as long as R1 is equal to R2, then I can say that there is no further movement of this particular radius, or actually r is not changing at all, right? So even at location P or at location Q, both are having a same distance from this particular origin. That means there is no linear displacement with respect to this origin for this particular particle, though it is moved from P to Q. Correct or not? Yeah, so it is zero displacement. Even though it is moving from P to Q, there is no linear displacement. So no linear displacement. But actually, this is having some rotational displacement, obviously, right? So this is having some rotational displacement, which is nothing but this displacement. So this is a rotational displacement. So we need to calculate that. So what is the methodology that we are going to adopt is, now these two vectors are one and the same because both are of magnitude r and both are in the radial direction. If you identify one more vector which is exactly in the middle, so let us say I call this as m, and this is nothing but r1 plus r2 by 2. So this is the vector usually. Now as r1 is equal to r2, this will again be r, obviously, right? This will again be r. Now if I call the angle between these two, or from initial position to the final position, if it is moved for an angular displacement of theta, then obviously this angle will be theta by 2. Correct or not? So from initial position to the final position, it made an angle of theta, because that is the angular displacement what we have applied here. Now here, this is making an angle of theta, then so this length, so let us say this is the perpendicular between these two. So if this is the perpendicular, then what is the length PQ? What is the length PQ? What is the length PQ? This length. We need to be calculating it. So this angle is theta by 2, and these two are actually perpendicular to each other. Then obviously this R1 multiplied by, so tan theta is equal to OM PM by OM, or PM is equal to OM tan theta by 2. And MQ is equal to OM tan theta by 2, or PQ is equal to PM plus MQ, 2 times of OM tan theta by 2. Correct or not? Got it? So this length is nothing but the perpendicular distance between these two, that is O1 getting multiplied by 2 times of tan theta by 2, where theta is the angle between the initial position to the final position, right? Correct or not? And this is having a direction of this one. Correct or not? So this is, if I call this as 2 tan theta by 2 into OM. So if I call this as, let us take one vector which is perpendicular to this OM like this. So like this particular chalk piece, if I take this OM vector, right? So this OM vector, I call this as K. So which is perpendicular to both X and Y, right? So this is a perpendicular vector. Now if then OM is a vector like this, OM is equal to R1 plus R2 by 2, and then if I can express this as 2 tan theta by 2 times K cross OM. So I have expressed the same thing in the form of the vector like this. Got it? So I have expressed in the form of the vectors like this. Now here this is 2 tan theta by 2 times of k is called as something called a rotational vector E getting multiplied by OM. So E cross OM is the rotational component. So Anubhav, so your question is here actually this is PQ, right? See. Now actually the way I have drawn the diagram to understand this particular format, usually the vector this one is drawn perpendicular to this. That is, it is making an angle of 90 degrees like this. Take this particular chalk piece. Take this particular chalk piece. And this is, let us say, this is the initial position and this is the final position. So initial position and the final position. Now here, draw a vector like this, which is my finger now. Now, complete from P to this particular O, draw a line like this. And from Q also draw a line like this. And then the angle between OP and OQ is angle theta. Now, this finger, if I bring it to like this, it is making an angle of 90 degrees, right? Correct or not? And then actually draw a perpendicular from this to this particular point or this particular straight line like this. So from the middle point of this chalk piece, draw a straight line which is perpendicular to this. Got it? So that's what is this one. So this way I have expressed. So because actually putting on the diagram is a little tougher. So this way you can understand that. A perpendicular drawn from this location. Yeah. Got it? So you try to interpret like this because actually the proof actually that is a little complicated. So if I take this as the origin, so this location, so this is constructed with a big diagram. So that understanding is a little tougher to bring out this particular configuration. So I have made a simplified form of it. Got it? If you want the complete proof, it is there in the textbook. How we can express like this, that is a little complicated. You try to understand that, but that is of no use. So I have simplified everything to a smaller part like this. So this rotational component understanding is important for us. Got it? If you understand this, that is fine. Got it? So the way it is constructed is, take this point as the origin somewhere below and take this chalk piece like this and draw a perpendicular to this particular line, exactly the straight line like this. Right? Now actually it makes an angle from origin to OP and OQ. That angle is theta. Based on that angle he will construct it. Got it? Okay. So this is the rotational component. So rotational component getting multiplied by this perpendicular vector is nothing but the displacement from P to Q, which is responsible for rotation. Responsible for rotational displacement. Right? So this is responsible displacement in the rotational format. That means as and when, if there are certain forces that are applied on a body, being is actually what we are analyzing is to be specific to the coplanar forces. Now we are applying certain set of coplanar forces on a body, then there will be an associated resultant force and there will be an associated resultant moment, and because of the resultant force there will be a linear displacement, and because of the resultant moment there will be a rotational displacement. That rotational displacement for each and every particle you will be able to find out with the help of this vector. Got it? With the help of this vector. Here if you notice, this part 2 tan theta times of k is independent of the particles. That means, suppose if I take this particular body like this, and let us say this is the origin, and I take one particle like this, and I take one more particle like this. Now let us say this body moved for a displacement of angular displacement of theta. Then let us say this is moved to a distance of, so this angle is theta, and this one also correspondingly moves for a displacement. So this angle is also theta. Right? Now only thing that is different between these two is this perpendicular distance between these two. This is different. So this part actually we have separated 2 tan theta by 2 times k is always constant for the entire body. As long as there is an angular displacement, depending upon the radial distance from the origin, the movement from here to here you will be able to calculate with the help of this formula. Now here, this E is constant for all the particles there because this is 2 tan theta by 2. If the body is moved for an angular displacement of theta, every particle is going to be moved there. Got it or not? So this is constant. Now only thing that is different is OM. OM is nothing but a perpendicular vector from this location. So this is the OM vector. So this is the OM vector for this particle. So like this actually you will be able to calculate each and every particle, the rotational movement component, how much it is going to be with the help of this E vector and the OM vector. Understood? Linear displacement is straightforward and easy. This is the rotational displacement. So rotational displacement actually you have to understand the concept of rotational component. That rotational component is this vector 2 times of tan theta by 2. Understood or not? Got it? Understood? Or do you have any questions on this? Yeah, theta by 2. Yeah, this is theta by 2. So let us take one particle which is at a location of P. Now it is moved to a different location of Q. Now here actually this is R1 and this is R2. Now definitely there will be some displacement both linear and angular, right? So this angle is theta. So this is having a linear displacement and the angular displacement. So this is called general displacement. In the case of general displacement, both linear displacement U and a rotational component of the displacement, that is E cross OM, right? E cross OM is the rotational displacement. So this is the total displacement vector. So U plus E cross OM is nothing but the total displacement vector which you can represent. So this is responsible for the work done. Essentially, this is entirely a displacement. Maybe rotational, maybe linear, but both are displacements only, not the angular displacement. Angular displacement is an angle, but displacement is nothing but a distance, right? Hence, here there is a linear displacement, there is a rotational displacement. So distance caused by the angular rotation, right? So now here actually this can be expressed as U plus E cross OM can be expressed as, OM is nothing but the midpoint between these two. So this is one position vector, this is another position vector. Obviously this position vector can be expressed as OP plus OQ by 2. OP plus OQ by 2 being M is the midpoint, right? So being M is the midpoint, OM is equal to R1 plus R2 by 2. R1 plus R2 by 2. Let R1 is equal to R and R2 is equal to R plus dr, let us say. So that means there is a radial distance of R plus dr. Then PQ is nothing but R plus dr minus R. This is the actual displacement change. So this is R and this is R plus dr. Now the difference between these two, or the vectorial difference between these two, is nothing but this is the PQ vector, because this is OP plus PQ is nothing but OQ. So that is nothing but that PQ is nothing but coming out to be dr, and this value can be expressed in the form of like this. See this. So if you simplify that, U plus E cross, so R plus dr by 2, U plus E cross 2R by 2 plus dr by 2. plus E cross R plus E cross dr by 2. So as E and dr both are so very negligible. So as E and dr are small quantities, we can neglect. So if you neglect it, so this is not going to be there. So we left with PQ is equal to or dr is equal to U plus E cross R. So this is what actually we are going to use in case of calculation of the work. So if there is an elemental displacement of dr, in that there will be definitely two associated displacements. One is the linear displacement, another is the rotational displacement. So that was caused by a rotational component of E, which is equal to 2 times of tan theta by 2 cross R. So this is a dr. Now when we calculate force into displacement, so in general actually work actually we calculate dW is equal to F dot dr integral. This is what actually we calculate. W is equal to integral F dot dr, but this dr is this one. Got it? It involves both U and E cross R. Got it? As dr tending to 0. If dr tending to 0, then actually this you can easily replace with U plus E cross R. Got it? Any questions on this? Any questions? Understood? So finally, what we are trying to analyze here it is, so we know that if there is a displacement, there is a work. So that displacement was caused by the force. Now, so the force can have two different components. One is the linear component, another is the rotational component. Now the work also, definitely there will be two different parts of the work. Total work is maybe certain quantity, but in that there will be certain work which was done just because of the linear movement, and there will be certain work which was done just because of the circular movement, right, or the rotational movement. The sum of both actually we will be calculating. For the simplicity purpose, we have expressed the elemental displacement as both the linear and the rotational component, so that you can easily find out the dot product with the force or the required force. Then you will be able to end up with the total work done if you use this particular vector. Got it? So that is the understanding. Clear? Or do you have any questions on this? Done? Okay. Now actually, so the work done by the force actually, if it is a linear displacement, you can straight away say that actually U dot F is nothing but the work done. But in case of there is some rotational displacement just because of the movement, then actually do we need to consider U also? That actually we will be discussing now. See this. Let a particle move from P to Q, which is having an initial position vector of R1 an initial position of R1 and move to Q and end position of R2. So that means it is moved from R1 to R2. Then because of the application of a moment of couple G, then the work done is given by F dot dr, right? Now here actually, so the moment is G, and G is caused by two forces. because this is a couple acting at R1 and R2 of magnitudes or of forces F1 minus F. Right? Obviously, so there is a force like this and there is a force like this, and this is the origin, and there is R1 here and this is R2 here. Right? So because of this, there is a couple of moment G, and this G was caused by F1 minus F. F1 minus F. Now actually, if we consider the work done, F into F dot U plus E cross R1, and another force is minus F, and then minus F dot U cross U plus E cross R2. This is the work done, right? This is the total work done, correct or not? Understood or not? So this is the initial moment and this is the final. Now U plus E cross R. So being this is the couple, there will be only a rotational moment. So because there is a rotational moment, even if U is there, it will not have any impact. That's what we are going to prove it. See this. F dot U plus F dot E cross R1 minus F dot U minus F dot E cross R2 is the total work done. Now this F dot U and this F dot U will cancel out because these two are opposite. So F1, F dot E cross R1 minus F dot E cross R2 is the total work done, right? Now here, so this is a scalar triple product and this is also a scalar triple product. Then actually what you can do is, you can take E out, E dot F cross R1 minus E dot F cross R2. So being scalar triple product, you can write the vectors in any direction, or actually in any point actually you can write all the three vectors. So because all the three are the scalar triple product, it will form. So one dot and one cross, three vectors. Now here if you take E out and then R1 minus R2 cross F. This is how you can express it. Now why we are expressing in this particular format is, now here the moment of this particular couple we can calculate, which is nothing but the torque, this vector cross product with the F. So that is, this vector is nothing but R1 minus R2. So this vector R1 minus R2 cross F is equal to G. This is the couple. Now if you notice, we arrived at R1 minus R2 cross F, which is nothing but the moment G. That means E dot G is nothing but the work done because of the couple of moment G. And in that actually, even if you consider U, it will not have any impact. As long as if the couple is moving a body, then the direct work done is nothing but W is equal to E dot G. This is the work. The way exactly we have done work for a linear displacement U dot F. Got it or not? So this is exactly the reason why we have calculated E. This is exactly the reason why we have defined E. So it is just an analogous for the linear displacement. So this is the rotational displacement analogous, which you can make use as if like force dot multiplied by U is nothing but G multiplied by E. Got it or not? So this is the work done because of the linear displacement. This is the work done because of the rotational displacement. So the sum of these two is the general displacement of work. Got it? Understood or not? Any questions on this? Understood? right? So you can note down this. So as and when actually there is a linear displacement, you can straight away say that the work is u dot f, and if there is a rotational displacement because of the couple, then actually the work done is e dot g. So E you can calculate as 2 times of tan theta by 2, which is the angle is from initial position to the final position of the particle. So this is about the calculation of the work in case of coplanar forces, right? So the new thing what we have learned from +2 standard versus now is there actually we will be dealing with only the linear displacement. So we are not considering the rotational displacement. So that is the complexity what is involved now, right? Now here the virtual work. So virtual work concept is, you understood the concept of work, right? Under the application of coplanar forces, what are the components that we should be considering and what is a work? Yeah, if both the rotational and linear is there, then actually it is the sum of these two. Got it? The sum of u plus f, sorry, total work is equal to u dot f plus e dot g. This is the total. So if you notice in all the cases, right, we tried bringing, whether it is a coplanar system of forces or non-coplanar system of forces, we always tried equating to one single force which is acting at a single point and a couple of moment g. So these are the two important fundamental quantities we brought from the system of forces, whatever may be the orientation it is. Now, once we arrived at those conclusions, we are making use of those conclusions to apply into this particular formula, and then actually we will be calculating the work. Got it? So the sum of all the things together will be simplified form of our work. Got it? So even in the coplanar force also, actually I have explained the theorems related to that, which says that all the system of forces can be bring into a single force, and all the system of forces can be brought into a single couple. So these two together will be equivalent to any system of forces, whether it is 2D or 3D. And those system of forces actually we are using here in the form of F and in the form of G. Got it? Jacket? Okay. So the principle of virtual work is there is something called stable and unstable equilibrium. Stable and unstable equilibrium, we mean, suppose actually if I hold this particular chalk piece like this, then actually if I move this chalk piece like this, then if I leave it, it will automatically come back to its original position. But actually if I hold this chalk piece like this, then if I move like this, then automatically it will try to fall down rather than coming back, right? So the first one is called as the stable equilibrium. Even if you give a little displacement, it will come back. This is the stable equilibrium. Suppose if I take this case, then actually if you move a little displacement, then automatically it will go out of the equilibrium case. So this is unstable equilibrium. This we are going to discuss in detail in the later session. Now here, in the case of stable equilibrium, what happens is, if a system of forces making a body under equilibrium condition, even if you give a little displacement, it will automatically come back to its original position. Correct or not? Suppose if there is a body like this, on this body actually there are multiple forces that are acting, still actually this body is under equilibrium condition even after the application of all the forces together. Now in this particular case, suppose if I give you a little displacement like this and leave it, so I have given a little displacement because of the force F, and then I will remove this particular force, then automatically it will come back to its original position, being this is the stable equilibrium. Now here, the application of this force and removal of that particular force, now once we apply the force, there will be a little movement. If there is a little movement under the application of the forces, then actually there will be certain work done. Now if you remove that particular force, then the work is done back. That means that is the negative work. So this is as if like the energy got acquired, and then actually it is releasing the energy again. That means essentially from the initial position versus the final position, it is exactly the same position. In such cases, no work done. As the system brought back to the original position. Because the system is under equilibrium. The system is under equilibrium. So if the system is under equilibrium, if you give a little displacement, after removal of the force, automatically it will come back to its initial position. Now essentially, there is no work done in such case. No work done. Now the displacement, initial displacement, whatever you have given, that is dr. This is called the virtual displacement. This is called the virtual displacement. That means if you give a virtual displacement, that means you are imagining that if I give a little bit of displacement, then being this system is under equilibrium condition, no work done even after I give the virtual displacement. And that principle is called the virtual work. That means even after I give you a displacement of dr, being this system is under equilibrium condition, it will bring back to the original position, hence no work done. Right? So work done and negative work is also done. So hence this is called the virtual work. Got it? So the work done just because of the imaginational virtual displacement is given is called the virtual work. Got it or not? So this principle is responsible for us to calculate the unknown forces. Suppose actually we know that these three forces are known and this is an unknown force, and then I have given a virtual display. Now I know that this system is under equilibrium condition, though I don't know this particular force of F4. And then if I give a virtual displacement, then if I use the condition of dw equal to 0 for the calculation of all the forces together, then I will get to know what is the unknown force, because I have got an equation. That is, so total F1 dot R1 plus F2 dot R2 plus F3 dot R3 plus F4 dot R4, and this so this one is coming out to be 0 because of the principle of virtual work. Got it or not? This is coming out to be 0 because of the principle of virtual work. So because this system is under equilibrium condition. So this principle we are going to use. If you know this one and this one, if you don't know this one, and these values anyway, based on the geometrical condition, you will be able to find out all these four values. The only unknown part is F4, which you will be able to find out with the help of the principle of virtual work. Got it? So this actually we are going to deal in detail in the next class, right? So it won't take much of time. So after this, I am going to deal with stable and unstable equilibrium. By end of this week, we are done with this statics part completely. Clear? Any questions on this? Got it? So that's all for today. Yeah, thank you. Good night.